We'll go through factoring. We have 4 examples of this also. The very first one, we just have 2 terms. So it's possible you have, if you remember all the different types of factoring, it's possible you have a difference of squares here. But we're going to take a look. We're going to start with just taking out a common factor. And to find a common factor, we got to look for common factors of each of the terms. So we have our coefficients, which are 6 and 9, and that does have a common factor of 3. So we know we can divide both of those by 3. Our variables here, they both have base x, so what we can do is we can divide by the common base to the lower exponent. And what does that mean? Well, x is to the power of 4, so we can divide both of them by x to the power of 4. And same concept holds for y. We can divide both of those by just base y. So our common factor is going to be 3x to the power of 4y. And then we'll see what we have left over inside the brackets, and maybe we can factor that further. So in this case, 6 divided by 3 gives us the value of 2. We'll write that in red. X to the power of 4 divided by x to the power of 4 is just 1. So that you can think of it as creating a 1 or even canceling out. And y divided by y also cancels out. So you actually just have the value of 2 left over from the very first term. In the second term, you have negative 9 divide 3. So that's actually going to give you negative 3. X to the power of 7 divide x to the power of 4. We've done that where that's just exponent laws. We subtract the power. So 7 subtract 4 gives you 3. So we have x to the power of 3. And finally, y to the power of 2 divide y to the power of 1. We subtract the powers. 2 subtract 1, and that gives us just the value of 1. When we look inside of these terms, there's not really anything we can do to simplify these two things. So this is essentially the factored version. We just found a common factor. So you'd actually, to write this, you wouldn't just write the common factor, you'd write the entire expression. In the second one, we can use a product and sum. You'll notice that the a value here is just 1, and it's actually 1 for all of these. So these are some simple factoring. So what we can do for this is we can find a value that adds to the middle term. So we'll label these. This would be our a, this would be our b, and this would be our c. We can look for 2 terms that add to b and 2 more terms that multiply to a times c. Now, because a is 1, anything times 1 is going to be itself, so we can just actually write this as multiplied to c itself. So we're going to look for 2 common terms. Sometimes it's easier actually to work with the addition. It looks like here, for multiplication, we know that 3 and 5 will work. So because 3 and 5 will work, we just got to figure out a version of 3 and 5 that will add to 8. And not just any 8, but negative 8 in this case. So because that's negative 8 and this is positive 15, if we make both of these negative 3 times negative 5 or plus negative 5 is negative 8, and negative 3 times negative 5 is positive 15. So those work as factors. So a very fast way of doing this now, because we have those 2 values, those can actually just become the second terms in the binomial. So we can have negative 3 and negative 5. This one here we can try to deduce the same way, but if you notice using special factoring, this is actually a difference of squares. And a fast way of doing difference of squares is actually just taking the square root of the first term and the square root of the second term, which happens to be 36y squared. The square root of the first term will just be x, and the square root of the second term is 6y. And because there's subtraction, hence a difference, we can actually write this in very quickly by putting in 2 sets of brackets. One will have a subtraction sign as the operator, the other will have an addition sign. And for the first term, we just write out whatever the square root of the value was. So we have x as the first term in both binomial answers, and we have 6y as the second term in both of those binomial answers. The only difference here is because it was a special case, we used an addition and a subtraction. The last one, we can use the same concept that we used in B. Look for 2 terms that add to 9 and 2 terms that multiply to negative 20. 5 and 4 work for multiplying, but because it's negative 20, that's actually not going to work for multiplication or addition, because that's not going to give us our value. One of them will have to be negative. Let's write another couple of sets of factors here. We have 1 and 20, 2 and 10, and 4 and 5. I don't think this one has a common set of factors. So a way we can check something like this is actually using a graphing calculator, because it can very quickly factor, or we can use the quadratic formula to solve this. Because it says to factor and not actually find the factors themselves, a way we can do this is we're just going to jump into a graphing calculator. We're going to punch this in to see if we get whole number solutions. If we don't get whole number solutions, then we kind of have to go through this a different way. And it looks like, yeah, no whole number solutions here. So a couple of things we can do. We can use a difference of squares to try to solve this. So what I'll do is erase the little bit of work we have, because we are running out of room here. Actually, yeah, that's right. So we know that the quick way is not going to work. So what we'll do is we'll actually use a difference of squares to do this. If you recall difference of squares, we divide the first term by the a value, which works out 5. The a value here is just 1, so there's no change to it. And then what we're going to do is we're going to take b divided by 2 and then square it. So b in this case happens to be 9. So if we take 9 divided by 2 and square it, instead of dividing into a decimal, I'm going to keep it as a fraction. It'll actually be easier to work with fractions as whole numbers. When we square it, we get 81 over 4. Okay? And what we're actually going to do is we're going to add and subtract that to the first two terms here. So we'll end up with x squared plus 9x plus 81 over 4 minus 81 over 4. And there's a reason I'm keeping it as a fraction. It's actually going to be a little simpler. We're going to take the negative value out, and normally you'd multiply that by whatever the a value is here. But since it's 1, it's not going to make any change when we go to the next line. So the next line is still going to read x squared plus 9x plus 81 over 4, then minus 81 over 4 minus 20. What's neat about this is we made a perfect square trinomial. And a perfect square trinomial, when factors, actually just one bracket to the power of 2, and you just have to find the square root of the first and the last term. So that's why I've let this fraction as whole number fractions. It'll be much easier to square root. The square root of x squared is just x. The square root of 81 over 4 is actually 9 over 2, the exact value that we'd originally started with. The operand, or the operator in front of the middle term, is a plus, so we'll bring the plus sign down. And then finally, negative 81 over 4 minus 20. We can find a common denominator to get this. Times 4 is going to give us negative 80 over 4, I believe. Yep. And when we subtract those two, we'll get negative 161 over 4 as a y value. So now that we've put it in this style, we can actually set it equal to 0. So we're going to need a little more space. And when we set it equal to 0, we can solve for x, since we've now isolated just for one x value. So I'm going to move 61 over 4 to the other side of the equation. So 161 over 4 is equal to x plus 9 over 2 squared. Okay. And now what I can do is I can find the square root of both sides. When I do that, the squared over here will cancel out, and we'll get a square root value. Off the top of my head, it doesn't look like 161 has a nice whole number, so we're going to leave that as a square root answer. So it's going to stay as square root 161, so we're working with whole numbers. But over here, what's nice is we can drop the brackets off. We have x plus 9 over 2. Now, when you square root something, technically you get a positive and a negative answer. So I'm going to put that plus or minus square root 161 over 4. Finally, I'm going to move 9 over 2 to the left side of the equation, so we'll get negative 9 over 2 plus or minus the root of 161 over 4. So that's actually two answers. And if we go back to what we were doing there, we end up with the exact values. If I put in negative 9 divided by 2 plus the square root of 161 divided by 4, we get 1.844, which is one of them. And if we do that with the other, and we just put a subtraction sign, we get negative 10. So that's exactly what that was there. And I just realized now, I don't think I was showing that part, so I'm just going to quickly scroll back up to show that process there one more time. We took the values, we started to complete the square. So we took b, which was 9, and we put 9 over 2 and squared it. Once we did that, we got 81 over 4. We substitute plus and minus 81 over 4 into the equation. We brought negative 181 over 4 outside of the brackets. This created a perfect square trinomial where we could square root the first term and the last term, which became x and 9 over 2. The middle operand comes down. So we've just very quickly factored that. That was the whole reason we went through completing the square. And then we simplified the values on the outside. We set it equal to 0 to find the roots. I'll scroll down just a little more. And because we've now isolated to just have one x value, there's only one x value here, I brought negative 161 over 4 to this side, became positive. We square root both sides of the equation, which cancels out this squared. We get plus or minus because the square root of an answer will have two values. And then we move 9 over 2 to this side, we get negative 9 over 2 plus or minus the root of 161 over 4. And then on our graphing calculator, we showed that that was exactly what was shown here. We just left them in root form so it was a little easier to deal with and work with.